Oh, hello. Wait, hello? Sorry, I just started myself. Hello. Hello, Yavi. Hello, Michelle. Hello, Avani. I don't, you can, wait, can you, am I on? Good afternoon. This means you can hear me. Oh, did I say Michelle? Yes, okay. Good. And does this mean you can hear me, right? Or am I on? Yes. Thank you. Okay. All right. So yes, good afternoon, Yavi. Good afternoon, Malita. Good afternoon, Amanda. Did I say that? Good after? Oh, there. Okay. I shouldn't laugh. That was a laughing with, not a laughing at. It was a laughing against. Good afternoon, Marilyn. How was my? Oh, how was my? Oh, it was that great. Thank you. Yes, that was very. It was. Thank you. Good afternoon. Hi, you. Oh, I said that too. Oh, I didn't. And good afternoon, Michelle. Okay. Yes, my birthday was good. Thank you. Uh. Oh, there's Melita. All right. All right. And okay. All right. Um. Okay. We are going to. We're going to continue. We are going to continue something I started last Wednesday, and we're going to finish it today. And then we're apparently going to go off to holidays, which I honestly did not realize. I thought well, it doesn't matter. Here's my question. Your lab 5, slow down. Hi, Chris. Good to see you. Yes. You did or did not yet already turn in the formal reports for lab 5, slow down, the inclined plane board.
Lab 5 is due this Wednesday.
Perfect. As in, great. Okay. Yeah, you told me that last time. I just couldn't remember. Okay. I mean, great. Yeah, and even though you don't have school this Wednesday, correct? Like you're saying, right? Okay. Then, even though I started this, so lab 5 is very important for a variety of reasons. Like there's, I, I so I started trying to address ways, hopefully clarifying issues to help you with your lab reports last Wednesday. I want to continue doing that today. Um, there are things. So there are things I have to say about the whole inclined plane problem that is involved in lab 5. Oh, you wow. Fell asleep during class. That's impressive. Wait, I'm not gonna take that bait, but that does have my attention. I will not fall asleep during this class. I can tell you, some of you might, some of you may every time for all I know. I have more to say about lab 5. I want to show you something about what you actually did in lab 5, and then I want to contrast it with a different way of doing things that you did not do in lab 5, but which dovetails with the board meeting that you did a couple weeks ago that I understand got confusing for people, et cetera, et cetera. What I want to say though is, so I have prepared things to say, as you can imagine. Some of them will be a little bit repetitive from last Wednesday, but what I'm trying to say first is, if there are any questions at all that you have about lab 5, if there's any way I can specifically address any specific confusions or clarifications or whatever that would help you write a better lab report, I'm here to do that. So I have a speech to give either way, for sure. In fact, the PDF for today seems to be like 24 pages long. It's not like I don't have things to say, but I really like to start off before I go down some rabbit hole that I'm going to go down. If there's anything that you want to put in the chat about lab 5 that would help for you to see me clarify, it may be that I'll just say, yep, that's exactly what I was planning to do. Don't you worry about it. But it may not. It may be that you're concerned about something that I didn't think to say. So I'm going to pause before I even begin and say, this is an opportunity, and it won't go away, but this is an opportunity. If there's something about your lab report or lab 5 or the basic issue that you want to put in the chat, please do, and I'll address it. Because yes, we're going to move on to topics when you come back from Thanksgiving, but that topic is pretty fundamental to physics, and it does appear Anyway, it does appear, it comes up later. So I'm gonna pause for a second. If you're unsure, just put it in the direct chat, obviously. And if I say, well, that's not really what I'm looking for, then fine. But if there's anything I can help directly with any confusions about Lab 5, this would be the time. So I'm gonna pause for a second just in case.
I have a question.
Oh, yes, okay, okay. Good.
Okay, so like towards the end of lab 5, it gave us like two equations. Well, it's the same equation, but it's like derived differently. So could you like go through explaining it?
I think so, depending on do you mean, are the equations you're talking about something like A equals G sine theta plus mu times G sine cosine theta, something like that kind of equation? Is that what you?
Oh no, it says coefficient of rolling resistance equals fric I think friction something. Rolling friction over newtons, something like that.
Okay, wait a minute. All right, I think, that's a very good question. Okay, hold on a second. I think I know what you're talking about. Let me, yes, hold on. How do I add a page once? Yes. I still don't know how to actually add a blank page, but I feel like, no, I don't. Wait a minute. Okay, yes, I'm totally gonna try to, I'm just looking to how to add I don't know why I don't know how to add it. Okay. Okay. Oh, that's how. Right. Okay. I think you mean this. Is this so? Does this look like what you're? And obviously, you could write them differently. You could rearrange. You could write like mu equals F over N. But is this the thing you're talking about?
Yeah, it's something like that.
Something like. Okay, that is a good question, and I'm gonna. I won't. Okay, so okay.
Oh, professor, I put the equation in the chat for you.
Okay. CRR. Okay. That they, huh. See, that's literally CRR, like, oh, okay, I think I see what. Huh. All right. Well, that's a rewritten version of one of these. That's literally how they wrote it in the lab, literally like that. Okay. I think I can address what I think is going on. I would not have written it exactly that way, but that's obviously everybody writes equations slightly differently. That's okay. What's going on there? There's a couple things going on. In general, the friction force exerted by one surface onto another, the friction force comes from two factors: roughness of material and how hard the two materials are being pressed into each other. So, like, this is just in general, not whatever kind of friction we're talking about. Friction. So mu in general, mu is coefficient of roughness. I mean, it's called the coefficient of friction, and there's different types, but really it's how rough the material is, and it's a coefficient in the sense that it has no units, and it's generally a number between 0 and 1. It's like a decimal or a fraction. So mu is like a rating scale of how rough a surface is in relation to another surface, and N is the normal force that one surface is exerting against each other. So number one thing I'm saying is, to know how hard one thing is sliding against another, you need to know two things. You need to know how rough the two things are, and you need to know how hard they're pressing against each other. If you multiply the two numbers together, the coefficient of roughness times the normal force, you will get the friction force. That's in general. And notice it works out like normal force is a force measured in newtons, and friction force is a force measured in newtons. So what we're really, another way of putting this is like the friction force measured in newtons is directly proportional to the normal force. But what is the constant of proportionality? The constant of proportionality, like the other factor that you have to multiply normal force by, is this number from 0 to 1 that represents how rough the surfaces are. So if the surfaces are not rough at all, if it was literally like a puck on air hockey cushion and there's like no roughness, then the mu would be 0. So it's like 0% of it. Doesn't matter how hard you try to squeeze the two things together, you get no friction at all. But if on the other end of the scale, if like we're talking about rubber on rubber, so the coefficient is like 0.9 or 0.999, then you multiply this force by 0.9 and you'll get how hard they're rubbing or sliding against each other. That's in general. So in general, we could say the coefficient of, like, in general, you can say, it's sort of like the equation you have written there, you could view normal force as an independent variable and friction force as an independent variable, sorry. And the greater one is, the greater the other is. And the slope of, like, the constant of proportionality between these two things is how rough the materials are. That's in general true about friction. And that's in a way what that equation says. However, the CR, like, so where it says friction divided by normal equals a coefficient, that's what I'm saying. It's like the ratio of, it's literally the coefficient of roughness is how many newtons of frictional force you're getting for each newton of normal pressure force. That's in general. Now, what I think is going on in your lab that they're pointing out is, and I'm going to bring this back to what like in the lab, our object is sliding along the plane. So, is moving. Let's say it's moving along the plane. If it were, it's moving along the plane. If your object in the lab, in lab 5, if you actually had like a little box or a little cube that was literally sliding up the plane and then sliding down the plane, if it were truly sliding, then we would be talking about kinetic friction, and the mu that we would be talking about would be the coefficient of kinetic friction, and the friction force would be mu times the normal, end of discussion. And let me say that basically for everything you do in the lab, we're acting like that's true. Like when we solve for the friction force, which I'll do in the free body diagrams in a minute or whatever, we plug in mu times the normal, which is the correct thing to do when one thing is sliding against another. The thing that you're talking about, the thing you're asking about, and it's a good question because other people this has come up with other people also. Like the truth of the matter is, in the lab, it's a lot easier to do this whole lab and to play and to repeat trials with a rolling object. Like in your lab, you didn't actually slide an object up and have it slide down. You rolled unless I'm mistaken, and tell me if I'm mistaken, but you rolled a marble up and let it roll down just because it's like so much easier to work with on so many levels. But the thing is that technically speaking, rolling is not sliding. The reason, and this is like, maybe I mentioned this in your class. Did I mention this on? Stop me if I already explained this in your class Wednesday, but it might have been the other section. The truth of the matter is, the reason we love rolling, the reason like wheels exist and ball bearings exist, and the reason like everybody loves rolling objects and puts cars on wheels rather than cars on blocks is because if you really think about it, the whole purpose of a wheel is to severely reduce the effect of sliding friction. Like the purpose of a wheel is the point of contact, the point at the bottom of a wheel that's in contact with the ground. The moment it's about to slide along the ground and like rub and experience this friction and slow down the wheel and the car and everything and lose energy and like blah blah, the minute that's about to happen, because the object is round, that point that's about to slide in principle sweeps up, like the wheel turns. So the point of the wheel, or the line on the bottom of the wheel, the part of the tread that was about to slide and experience friction, moves away and a new line comes in. And then when that's about to experience friction, it moves away. I don't know if this makes sense, but the whole purpose of rolling is actually to get rid of the sliding effect. So if you had a perfect roll, the kind of friction that's actually acting on a perfect roll is not sliding friction. It's actually the other kind of friction, static friction. Static friction is the kind that tries to stop an object from sliding at all. Static friction is what tries to hold an object in place. And ironically, it's really weird to think about. So, I mean, if people in the class don't get all this, it's okay. But like the whole purpose of a wheel is actually to trade kinetic friction, sliding friction, for what ideally would be static friction, and then would be a much, much smaller value. But even sliding, I'm sorry, but even so what you're doing in the lab with rolling a marble, you're not strictly doing kinetic friction. You're strictly doing something closer to static friction. But now here's the final but. But even rolling is not perfect. Why is rolling? Even rolling doesn't perfectly eliminate sliding, because even round objects are not perfectly round. All round objects squish a little bit, like they all have weight. Gravity pulls round, like even your marble, gravity, its own weight is pulling it down on the inclined plane. And honestly, on a microscopic but actual measurable real level, it's squishing a little bit when it sits on the inclined plane. It's not just one point or one line that's tangent to the plane. There is a little bit of depression and deformation that goes on. So a little bit of sliding does occur, a lot less than it would if it were a block, but a little bit of sliding friction does occur. And that is actually what we're measuring. And it's enough to make the whole lab work. It's enough. There's enough friction that makes the ultimate conclusion of this lab, which I hope everybody knows at this point, the ultimate conclusion of this lab is that marble takes more time to come down than to go up, right? Which is supposed to be a surprise. Like, and I hope it's clear now that that is what goes on, but I hope it's also clear that that is, I don't think, expected. That I'll say it again, the marble takes less time to go up than it does to come down, i.e. it goes faster on the way up than on the way down, entirely because of friction, because there is just enough sliding friction even on that marble to make this whole effect true and to allow us to treat it as though it's sliding friction. The thing that you're asking, man, I'm going to move on a minute. I know this is a lot of information, but it is a fair question. And I said I would answer any question, so I'm trying to. So when they give you that CRR equals FR over N, what they're saying is the coefficient of rolling friction is the friction force divided by the normal. The rolling friction coefficient is kind of like a lie. It's like a number we make up. It's what we're saying is it's the number that allows us to treat this imperfect static friction as kind of a very low grade, low level, but functional sliding friction. Rolling friction is like a compromise idea between static and kinetic, but the number that we give to it then works just like any of these other kinds of friction. So, I mean, so what they're really trying to tell you, that, and then I'm wrapping up, they're trying to tell you that it is okay to use the equation friction equals coefficient times normal force, which we are totally using in the lab, that the friction force equals the coefficient times the normal force. Like, that is the takeaway of that as far as I'm concerned. And they're, by giving it another extra little equation, they're just sort of admitting that this kind of friction that's going on is a little bit funky and a little bit weird because technically it's coming from a rolling object, not a sliding object. Does that make any, I know it was very long, but does that like address what you're asking at all? It was a very long,
Yeah, makes sense.
okay. All right. Well, thank you. Okay. Thank you. I know that was a lot. I'm working on the not a lot thing in my life. Any other, but is everybody clear? Is everybody, I'm going to like do it my way. I mean, I could still take more questions if you want, but if everybody's afraid that I'm going to go off, is everybody clear that the punchline, that the goal of the punchline of the lab is something, if you send something on a natural round trip in a controlled but realistic circumstance, right? Like that's what the lab was supposed to be. It's controlled, but it's totally realistic. You're just sending something up a rough everyday plane and it's coming back down the plane. Like this could be literally what you did in the lab, could be a child on a slide in a playground. And believe me, I used to test this and you've met the child. Like you could push a child up a slide, they come back down. And if you actually time it, because the child is realistic and has friction between the child and the slide, the child will actually take more time to come back to you than to go away up the slide. And it's even actually more, I mean, the slide, if it gets too steep, weird things start to happen. But if the slide is reasonably shallow, the same thing will happen in a playground as what happened in your lab. And actually, it'll be even more vivid and more clear because it's 100% sliding friction then and none of this rolling weirdness. So Matt's looking, I see there's something in the chat, which thank God, thank Cork. But the ultimate punchline of the lab is that it takes more time to come down and then to go up. And your job in the lab report is to show how that surprising result actually makes sense if you break down all of the component diagrams. If you break down all the free body diagrams into component diagrams and then use F net equals MA to actually solve the diagrams, you can show that fact. I mean, that's what you're trying to do in the lab. I hope, and I'm going to do that again now. I'm going to break that down further now, but I hope it's clear that's what you're trying to do. Okay, wait, let me look at the chat. No, we should. Back in it. I'm telling you, before COVID, we used to have all kinds of labs and all kinds of crazy playgrounds and with, I mean, but yeah, we should. Yeah, tiniest goes for. Whoa! Oh my God, Yvonne. Whoa, what? Okay. Yes. One day I'll take you up. Go to. Is there a judge? Oh my God, why is my? Oh, sorry. There's a John Jay playground. I don't even. Oh, the one across. Oh yeah. Okay. So yes. So that's the point of the lab. Now I'm gonna go. So your job is to show with the diagrams and everything why the surprising punchline is true, right? So, and it comes down to the components of the free body diagrams and the solving F net equals MA. So what I want to do here is I want to start with where I already was on Wednesday. Like this is going to be a little bit of like review, but then hopefully it's helpful to people. But my main goal at the beginning, as the title says, I think one of the hard parts of all of this, the confusing parts, is like why we broke up gravity, and not only why we broke up gravity into sine and cosine rather than breaking up something else, but where did I get that one particular component was sine? How did I know which one is sine and which one's cosine? I know I started explaining this Wednesday. I want to say more about it today, but I want to say again, of course, I'm not grading your lab reports, but there is usually a problem like this on one more exam that we have to take. And I'm telling you now that the best way for you to explain the kinds of things that I'm about to explain right now, and the best way to understand them for Physics 204 and for your future, the best way to understand these things for most of us is to first acknowledge honestly that there is some kind of confusion or something to be understood. Like I'm telling you, I think it is confusing at first that we break up gravity. I think anybody who sees that it's confusing at first is being honest with themselves. And I think it's confusing how we know which one is sine theta and cosine theta. If you think it's 100% obvious that we would break up gravity and 100% obvious which one is sine, which one's cosine, I think if you always have and you never even had a moment of thought about it, I think something that's a little bit unusual, to put it mildly. Maybe you get it. So I'm going to explain. So here we go. This is if we were going up the rough inclined plane, if we're going up the inclined plane, given that picture that you see on the board right now. Oh, wait, there's something else in the chat. So that's just my picture of the way my plane is oriented in my mind. Well, okay, actually, I really appreciate what Chris put in the chat. So Chris put in the chat, isn't X cosine and Y sine? I'm very glad he put that. And I'm saying this with total respect to him. No, the answer is no. The answer is that's what people tend to think until this point in math and physics. That's one of the reasons I think this is confusing. People tend to think that X is cosine and Y is sine. And there's good reason to think that. Like on a unit circle, that's definitely true. In the unit circle, that's the original definition of cosine and sine. But once you have right triangles, cosine goes with adjacent and sine goes with opposite, and that's not always X and Y. In fact, and this isn't a technical point. This is a huge point that really confuses people in physics. So like, I'm totally glad that Chris is like, this is what I mean. Like this discussion only makes sense if we admit like people tend to think, and I did, that X goes with cosine. But we're here in physics now where the big principle is that we get to choose our coordinate system. And it turns out to be really important in physics that we make conscious choices of where our axes are and what our axes are doing. And depending on our choices, it's not always clear even whether X is horizontal or not. It's not always clear that X goes with cosine. And it's not even always clear what's adjacent and what's opposite. So I'm glad he asked, but that's what I want to show you right now. That in this case, for example, it's not, I think in this case, we're going to see that X doesn't go with cosine, and that's why it's confusing. So, I mean, great. And that's my point, that I'm a genius. Yes. Okay. So here we go, though. So here's my picture. But keep those questions coming, all of you, seriously, please. So here's my picture, the blue picture of like where the plane is oriented in my mind. So then I draw, now I'm picking the example where the thing is going up and there is friction. So the friction is pointing down. So here's my pure free body diagram right underneath it, right? The normal forces from the plane going off perpendicularly to the plane of contact. As you know, gravity is pointing straight down, as you know, and the friction is perpendicular to the normal force going along the plane. So that's my pure free body diagram, like we said last Wednesday. Now we look at it, we realize, oh my God, so, oh my cork. Some of the forces are not parallel or perpendicular with the others. Like somehow, not, no matter how I think of it, not all of these forces are along a clear X and Y axis. So so at least one force is going to have to be broken up into components along the X and Y axis. And the big thing I want to say first that people always skip is if you're going to break up any force into X and Y axes components, and you're going to choose what force to break up, the way to choose that is first you choose what are my axes? What coordinate system am I looking at this through? And it's a choice. And the real principle is that any coordinate system you would pick should get ultimately the same physics laws, the same physics results. But some coordinate systems are going to be easier to work with than others. And this is the whole issue of physics. This is where physics is not just math, it's physics. So what I'm saying is we have a choice. We can look at a coordinate system that's like this, like regular, everyday, conventional, customary, horizontal and vertical, or we could tilt our coordinate system. I mean, there's a lot of other things we could do too, but the two most, I think, straightforward options are we could keep our coordinate system like this, or we could tilt it like that. Now, I'm going to say, first of all, like I said Wednesday, that in this case, I'm going to say that our strategy that I'm trying to teach you as a strategy for future topics and future classes such as Physics 204, I want to show you that the strategy, the conscious choice is tilt your coordinate system so that your positive X axis lines up with the expected direction of positive acceleration. Now that is a strategy, and it's such a subtle strategy that part of what I'm trying to show today, I'm going to repeat myself a little bit from Wednesday and show you the strategy, but in order for you to really see that it is literally a strategy, is that by the end of the class, I'm going to do the other choice as well, and you are responsible for it. I'm first going to show you what happens when we do the strategic thing. Then I'm going to show you what happens when we do the, I think, less strategic thing. And if you're following along with me, you'll see that both are going to get the same answer. And this is the power of physics. Both will get the correct answer. But the second one, even though it will seem more natural and obvious and less weird at first, will become much harder than the first. And this is why we're going to get used to this strategy. So what I'm saying is we are going to choose to line up our x-axis with the direction of acceleration, which means tilt our coordinate system. And I'm going to look in the chat in 1 second, which means I'm going to tilt my head and go like this, which is already like a weird thing to do. And then if I do that, if I tilt my head like this, if I say this is my x-axis and this is my y-axis, that means that in the original picture that I drew like 2 pages ago, that means that gravity, which seems perfectly ordinary, like just straight down, like what's the problem? Gravity's fine. Like what? Under this coordinate system, gravity is a problem. Gravity is not along a y or an x-axis, so it's gravity that has to be broken up. I'm going to pause for. I'm going to look in the chat in 1 second. What I'm going to say. This is beat number 1 in this whole argument or whatever. Is that I think that if I didn't have a reason to, of course I wouldn't want to break up gravity. I like it does seem weird at first and unnatural to make gravity the hypotenuse of a triangle. But what I'm arguing is we're gonna make that choice because it's gonna lead to much less work than not making that choice. So under this choice, MG has to be resolved. So I'm gonna zoom in on MG on the next page, but first I'm just looking at the chat. Wait. Oh, it was already, sorry, I'm a genius. Yes, totally, of course. Okay, so I'm gonna zoom in. Okay, so here I'm zooming in on MG, the brown, like the long vertical line. And by zooming in, I'm saying that is a vector of any vector is really secretly the hypotenuse of its own right triangle. Like any vector in life of any kind, like does something along the x-axis plus doing something along the y. So I'm going to break up gravity into an x and a y. And notice I'm being very careful, like x, I draw an arrow along an x-axis, and then from the tip of that x arrow, I start the tail of a y arrow. And notice, literally, like if you practice, this is where you really want to practice on your own. If you practice on your own and did this, you'd see there's a million different ways you could break up gravity. Like there's a million different ways you could orient this triangle. But I'm specifically orienting it with respect to the plane. I'm saying that gravity seems to be the weight of an object pulls it straight down to the center of the earth. There's no changing that fact. But if you put an inclined plane in the lab, I mean, you put a slide in the lab, what are you doing? You're now making a situation where gravity, by pulling straight down, is actually doing 2 jobs. I'm saying that down is actually the sum of down left plus down right. Just like in Manhattan, like in regular vectors, like northeast is the sum of north plus east. Down is the sum of down left plus down right, or more specifically in this case, as the English is trying to say, by gravity pulling the object straight down onto a tilted plane, it's to some extent pulling the object along the plane, but to some extent pulling it into the plane. Those are the 2 jobs of, or the 2 implications, or the 2 components of down. Down along plus down into, or down against, if you like. So one of those components is mg times the sine of theta. The other is mg times the cosine of theta. But the big, right, so that's the first thing. And I've broke, again, one of them is the x component, one of them is the y. The question is which? And now here's where we have to do a little work. This is where I said the answer I know last Wednesday, and you already know the answer from lab. I know that, but I want to break this down more slowly and show you why for 1,000 reasons. What I want to say is, and someone like someone literally said in the other class, and this might relate to some of you, someone said in the other class that the reason they were confused is because they felt like they were given the angle in the lab, like they felt like they knew the angle of the inclined plane. But it felt like we were doing all this work solving for the angle, and they didn't understand that because they thought they were given the angle. So why are we spending time solving for the angle? Great question. I don't know if any of you can relate to it, but it's a great question. What I'm here to say is that's exactly the point. That's right. You were given the angle in the angle you're given, the angle you know, is that blue one right here on this page. The angle, like it says, given the angle between the ramp and the horizontal, that between the ramp and the horizon line, the table, that's called the angle of inclination, how steeply the plane is inclined up from the horizontal. Now, sidebar, you could have been given the other angle. You could have measured, you could have been told the angle up at the top of the plane. And if you were given that angle, every single thing I'm about to say would have a reverse answer. Like everything I'm about to say about sine would be cosine if you were given that, and vice versa. Which is, and sometimes on final exams, that's what we do. I mean, not to like be weird, but I'm just saying, like, you don't want to memorize sine or cosine. I'm trying to explain to you how we got them, because it's based on what we originally think the angle is. We were given this original blue angle here, measured from the horizontal. What we want is to know, where is that given angle in this triangle? That's the tricky part in a way, or it's a tricky part, is I now have this vector triangle and I'm trying to find out which side is sine of theta and which is cosine of theta. But the only theta I have to work with is the one that I'm given in the lab of the original plane. So my goal right now, like literally my goal right now, but like sort of your goal when you're in the lab, is to figure out in this rotated weird triangle, which one of these two non-right angles is the same as the theta that we originally were given. That's the question. So hold on. So I do a little geometry, right? I'm just gonna I do a little geometry. Like there is that triangle blown up, right? The big black triangle is the triangle I'm talking about. But if I place like a imaginary horizontal across it, like the lab table in red, then you can see maybe, okay, now we have a new right angle. Like there's a right angle between the two vector leg components. That's definitely a right angle by definition of axes. But then there's also a right angle between the vertical line of gravity and the horizontal red dotted line that I just introduced that represents the lab table. So what I'm saying is, oh, okay, if now I can see where our original theta is, our original theta that you're given in the lab is the original theta that you know is this thing right here that I just circled, right? That's the original theta. Well, if it's right there, then what am I trying to say? If that's the original theta, then this thing up here cannot be theta, right? This is now a right triangle. So if this is theta right here, then the other angle in the right triangle is not theta. It's the complement of theta, right? It's 90 minus theta. But then that means if I zoom out and look at this whole big right triangle here, then the angle at the bottom of the big right triangle is not 90 minus theta. It's 90 minus theta. I don't know if this is a lot of words. This is a lot of words. But I'm saying if I believe that this is theta, the original theta right here, then that must mean that this right here is not theta. It's the complement of theta. Therefore, this down here is theta. Stop me if you don't understand that. Or actually, can you just raise your electronic hand if you do understand that, honestly? Like, okay, that's good. That's Avani and Chris. All right, sounds good to me. Thank you, Avani and Chris. Okay, all right. And I think Melita, I'm just going to assume that Melita's totally with me. But no, wait, do you want me to? Okay. Do you honestly see, do you see that? And thank you for your honesty. Do you see that this thing that I'm like chicken scratching, do you see that that's the original theta from like, that is how inclined your inclined plane is? Like, okay, then my argument is that this is a right triangle, like the inclined plane itself, you could picture as a right triangle. And if this is 90 and that thing, that black mess is theta, like all the angles of a triangle have to equal up to 180 degrees, right? And this one's already 90. So the one up at top has to be 90 minus theta. Does that make, like, honestly, Melita, is that, like I'm saying this right here, this is 90 degrees minus theta. Does that make sense or no?
Yeah, it makes sense, but we're saying that the two thetas are the same.
Oh, well, I'm saying, okay, this is what I'm trying to get at. I'm saying when I say theta, whenever I say theta, yes, I mean the original theta that you know from the lab. Yeah, when I use the word theta, I'm saying it's the same as the original theta. But that's what I'm trying to find out, where is that theta in this whole triangle? Like what angle is he? And so my point is that I think this, like, I think, let me get a highlighter, hold on. I think this is the original theta. Like it's literally looks it is how steep something is from the horizontal. Like that literally is the original steepness of the plane. So therefore this thing is not the same as theta, but it is 90 minus theta. Because if this is a right angle and the angle to the left is theta, then the angle above, are you with that or no? Or is it, but then I'm zooming out and saying, well, this is all one big right triangle, and with the big right angle being all the way to the left. Therefore, if the top angle is 90 minus theta, then the bottom angle of the whole big triangle must be 90 minus theta. Like the bottom angle of the whole big triangle is the complement of the top angle, but the top angle is the complement of the side angle. Does that, yes or no? For real?
Yeah, it makes sense. Thank you for explaining.
No problem. Okay, okay, and you're not alone. I promise you, you're just alone in having the guts to say anything. Really.
I have a question.
Oh yes. Okay, yes.
Okay, going back to like what Melita said. So how was it 90 minus theta? Because I thought like in a triangle, all the angles add up to 180.
Right. So you mean how is the top 190 minus theta? Because
Like, don't you have to divide whatever theta is by 2 to get all 3 angles?
wait, but the third angle is a right. Wait, let me draw this again. I'm glad you guys are asking. Hold on, let me add another page. Oops. I know there's a way to do this.
That's what I remember from geometry class.
Yeah, no, you're right. You are right that all the angles have to add up to 180. Absolutely. So here we have. So the original, what we have is this. Okay, this is our vector triangle. Like here's gravity going straight down. Here's one vector. Here's the here gravity is the thing going straight down. And we know that this thing is a right angle. The one thing that this is a right angle because it's the angle between the x-axis and the y-axis. Makes sense so far? Is that fair so far? Or yes or no? Okay, so that's a right angle. So I'm saying this big triangle is one big right triangle. So that's 90. So all the angles have to equal up to 180. Yes. So that thing is 90. So that means these two together have to add up to, like we've already subtracted 90 from 180. So there's 90 left over. These two together have to add up to 90. And in fact, I'm claiming that that's always true in all right triangles. Like in all right triangles, the two angles that aren't the right angle, they always have to add together to make 90. Is that fair so far or no? Okay, that's yes, Chris, but Melita, yes, no, yes. Okay, so then I'm saying that here's the trick. Here's the part that may be throwing everybody off. I'm saying now I come along and I introduce and I say, that's my big gravity vector triangle. But if I picture the lab table to be right here, right, which I can because this line, this vector is supposed to be the plane. Like this is where the marble is sliding along that thing. And if I just compare it to the floor, the lab table, right? The angle between that x-axis, the angle between that and the horizontal, remember we've tilted our x-axis. So our x-axis is no longer on the horizontal, but the amount we tilted it by, the amount that we tilted the x-axis away from the horizontal is what we mean by theta. That's the original theta is right there. I'm not saying the whole right angle. I'm saying that portion of it. Like theta is, sorry, I'm standing up. You can't even see. Theta is how much we tilted the x-axis up away from the horizontal. Makes sense so far or no? Like honestly, or like, and you can like unmute you guys, like seriously. Okay. So then if I just did that, then I'm saying, oh, we have a new right triangle here. Like this is also a right triangle now. It's a different one. It's not the same as the big one. This is a different right triangle now. But if this is a right, so if this is a right angle right here that I just like filled in, and this guy here is theta, then within this right triangle, by the same rules we said a second ago, then like these two angles, like theta plus this guy must together equal 90 degrees. Does that make sense or no? So,
Yeah, that makes sense now.
Oh, for real? Okay. And Melina, for real, for as long as you're, I'm not like trying to, but as long as,
Yeah.
okay. Cause then I go one more step and then we're done with this. I'm saying if that's, and yes, this is like, that's why I'm explaining this. I don't think that, I think this is true. I don't think it's obvious. That's why we're talking about it. But I'm going to go one more step and say, but wait, now look, now I've got a whole big, the original right triangle that we were looking at, this whole big right triangle here, for which this is a right angle, like this whole thing, the angle between the x-axis and the y-axis. Then I'm saying, oh, if that's one big right triangle, and this guy up here is 90 degrees minus theta, well then, then the other thing must be theta, because those two together, the top and the bottom thing together must make 90 degrees. Am I making any, does that, for unmute, no, yeah, sort of. I mean, good enough for government work, or yeah, Melina?
Sorry, I don't mean to be annoying. I'm just still confused, like, because if you have three angles and we know the bottom right corner, that's the 90 degrees,
Wait, the bottom.
right?
Wait, the bottom right. The 90 degree.
Like across from MG, where MG is written, so like next to that.
Okay, yeah, like here, I'll do a new color. Like, you mean like this thing is 90? Is that what you're? Yeah, that thing is.
No,
Oh, this thing.
yeah.
Okay, that's
So we
90.
know that that's 90.
Yes.
And then are we saying because we know the other, but like, can't we say that we know the other one is 45? So then can't we do 90 plus 45?
Wait. Which one can we say is for? Wait, that may be the where I don't. No, I don't think we could say any. It sort of looks like 45 in this diagram because it sort of looks like this Y side and this X side look pretty much the same, but that's sort of an accident of this diagram. I don't have any reason, like maybe I should draw it again, but I don't mean for this leg and this leg to be equal. There's no reason for me to assume that those two angles, one of them would be 45 only if I knew that both of them were equal, but I don't actually believe. The truth of the matter is it's like super exaggerated. Like in your lab when you did it, here, I'll make, like the angle is like really very not steep at all. It's really like this. So maybe this would be a bit, maybe that's what's confusing in the diagram. Hold on. So it's really like, right, like, it's very not equal. So this is a more exaggerated version of the diagram. So I don't know if this is what I'm trying to say here. Does this help at all that if I exaggerate? Like, I don't think those angles are 45. That's
Yeah, makes sense now.
oh, okay. All
Thank
right.
you.
No, thank you. And guys, everybody, honestly, it's not annoying. And anybody, like, it's not annoying. It's like, it's class. Like, I really appreciate anybody, whether it's Melita or Chris, and everybody has a different style, but like, it should be about you guys. It's not supposed to be about me. Like, like, and it takes guts for them to stop me and stay on that. And even those of you who think right now that you already get it and like you want to be hearing about something else, fine. But then when it's your turn, then take your turn. Like when you know what I'm saying? Like it's their turn now because they're saying something, which is to their credit. But okay, anyway. Oh, okay. Yeah, that's funny. Now that is true. The funniest thing is I shouldn't admit this, but wait, you're about to have lab, aren't? Oh no, it's Monday. Anyway, I'm in John Jay right now, actually. But anyway, all right. And I'm looking at the time. I'm sorry. Yeah. Okay. So all of that is to say that I believe that the angle that is the original theta is down here in the bottom of this diagram. And that then means, I'm going back to the diagram. That then means right, that if I believe that the angle is down here, then this x-axis is opposite from it. And this y-axis is adjacent to it. And that's a big revelation because on it, like, am I saying you have to go through all of this work every single time? not necessarily. I might be trying to give you a trick by the end, so you don't have to go through all this work every time. But I am saying somehow we had to think about this and find that the angle is down here. And that means that actually mg sine theta is going along what we would call here the x-axis, which is a surprise. It goes back to Chris's original question, which wasn't a crazy question. Like I'm saying, if you follow this geometry, then mg sine times theta is the side that is the vector component that's going along what we call the x-axis, and mg cosine is going along the y-axis. So now, and we're literally saying mg sine plus mg cosine together equal mg. Excuse me. So it's like if you walk northeast in Manhattan, or if you need to get somewhere northeast, what you do is you walk some amount east and then some amount north, and you add those two vector components together and you get your total. Like you'll end up at the correct place if you do a certain amount of avenues and then a certain amount of streets, right? Same thing here. If we go back into the original free body diagram, instead of drawing mg down, we draw its components. We draw mg cosine theta along the y-axis. We draw mg sine theta along the x-axis, right? And now we have components that are only along axes. So now we can solve. Like this is just for the up trip, and you do the same type of thing for the down trip. And in the down trip, you find all the same analysis, except friction flips the other way. But when we're sorry. Okay. So but I want to really make this more physical, because that's like a lot of geometry. And obviously some people are getting concerned about the geometry. Let's take a step back and just look at this physically. Let's physically consider what I mean by mg sine theta. Like, don't even worry about friction for a minute. We're saying that mg sine theta is the component, the fraction, like sine and cosines are always fractions, right? So mg sine theta means mg times some fraction. It's some fraction of the weight of the object. Some fraction of the weight of the object pulls it along the inclined plane, whereas another fraction of the weight pulls it into the inclined plane. We're saying the fraction that pulls it along the inclined plane is the sine fraction. What the heck does that mean? Well, think about it if there was no friction. Just get rid of friction in your mind for a second. Assume that mu equals 0. Then mg sine theta would equal ma. Right? Like the net force, like if there was no friction, if you look at this diagram, if there's no friction, then there's only one force along that direction, and it's the mg sine theta force. So mg sine theta would equal ma. You could divide both sides by m and you say g sine theta equals a. What does that mean? It means the rate at which you'd accelerate down the plane is some percentage of g, right? It's some fraction of g, whereas g is like 9.8, like free fall. The free fall rate of acceleration, right? So we're saying that how fast you go down the plane is some percentage of 9.8, and that percentage gets higher and higher as the angle gets steeper and steeper, because sine of 0 is 0, and as angles get bigger, the sine gets bigger. Sine is super that way. Sine makes sense that way. Well, like that's what this says. I'm going to skip this page in a second. I'm going to turn the page in a second. But like it says, A equals g sine theta means the rate at which the object accelerates down along the plane is the sine fraction of g. I'm going to just go to the next page because it's much clearer. It's the same thing, but it's just much clearer. Look, make a chart in your mind. If theta is 0, then A is g times 0, which is 0. Doesn't that make sense? If the plane is flat, if it's purely horizontal, gravity isn't accelerating the ball along the plane if the plane is flat. So if theta is 0, sine of 0 is 0, and A equals g times 0. A equals g sine theta. If the plane goes up to 30 degrees, the sine of 30 is 1/2. So it's g times 1/2. 1/2 of 9.8. Like 50% of free fall. If the plane gets higher to 45, then it's like 71% of free fall. If it goes to 60 degrees, it's like 80. Where am I getting these numbers? I'm doing like square root of 3 over 2 or square root of 2 over 2 or whatever out. Like that's where I'm getting these numbers. I'm just saying, so of course it makes sense when you step back and look at it. it really makes sense that the sine of the angle times g is what determines the acceleration or the force along the plane. The force along the plane gets bigger and bigger as the angle gets stronger, whereas the other one, the mg cosine one, does the opposite. It gets weaker and weaker as the plane gets more and more inclined, right? The plane supports the ball less and less as the angle gets bigger and bigger, because cosine of 0 is 1, and as angles get bigger and bigger, the cosine gets smaller. You can think about this more later when you get home. I'm ultimately saying that it actually makes sense. And wait, I just want to see. Oh yeah, I'm ultimately saying once you get used to this, if your big problem in physics is, I get that I'm supposed to divide this up into sine and cosine, but I don't know which one is sine and which one is cosine. If you get to that level in physics where what you're concerned about is which one is sine and which one is cosine, then join the club, like welcome aboard. Then you are doing physics. Like, don't think that means you don't understand anything. It means you're confused about exactly the right thing. If you don't know, if you know how to get to that point of breaking up and saying one of these is sine and the other is cosine, but I don't know which is which, then actually what I'm saying, you could do a lot of geometry like we just did, or actually when you get used to this, you could just back up and say, oh yes, sine of 0 is always 0, mathematically. So physically, whichever vector arrow would disappear wouldn't be there, would be equal to 0. In the case of theta being 0, that's the one that should take the sine. You might have to think about that a lot at home, but once it clicks in your mind, it's a technique that's always true and always works. It's not that sine is always x or cosine is always x. It's that sine always goes with the thing, the component that should disappear when theta equals 0. Because sine of 0 is 0. And when theta is equal to 0 in this case, the component of weight that pushes us along the plane should disappear. When theta equals 0, we're not pushed along the plane. We just sit there, right? We don't slide. There's no reason to slide. So the component that goes along the plane gets sine. Again, you may have to think about that, but that's what I'm saying. I'm going to move on to say, but I do see there's something in the chat. Hang on one second. No. Yeah, there's a lot. Actually, what Chris just put, like the part he put in after the Felix, there's actually a lot of wisdom in that. I mean, I'm not going to dwell on it because I have to, but yeah, like remember I told you this on the first day. What's really weird about physics is hard because it's simple. Like for real, the opposite of easy is hard. The opposite of complex is simple. The opposite of hard is, you get what I'm saying? Like, yeah, physics is weird that way. But okay, I'm going to keep going. Right, and that's how Chris is a genius. Yes, that's the real lesson of this. All right, so we put those both in the FBD, and then we have to solve. I'm just looking at the time for if you're doing your lab report. Right, we've got 20 minutes. If you're doing your lab report, that's your FBD for the up trip, your component FBD for the up trip. And then what you do is now you separately, you independently but simultaneously apply F net equals MA to each axis one at a time. So first you go to the y-axis. Oh, I always go to the y-axis first, the axis that has the normal force. And we say, okay, normal up. I mean, I'm just looking at the diagram. We've got normal going in the positive direction. We've got mg going in the negative. So we're just adding them up. Normal and mg cosine theta. But mg cosine theta got a minus sign because it was going in the negative direction. So n minus mg cosine theta equals ma in the y direction. But now, here's the thing. Because again, notice all the work and all the thought, if your brains are numb or whatever, are comfortably numb, it's because of all the thought we just put into like the physical arrangement of the situation. We now are ready to do the algebra. Like, we haven't been stressing over algebra. We've been stressing about setting up the algebra. Now we're about to do the algebra. And my argument is, or my position is, the algebra itself is now going to be deceptively easy. So easy, comparatively speaking, so straightforward that it would be easy to think it's the only way to do things. Like, for example, I'm going to say now that the acceleration in the y direction is 0. Now, what do I mean by that? I mean, the object is accelerating and it is falling down, but y-axis is not straight up and down according to the way that we're choosing to do this. Our y-axis is going off at an angle, like in the direction of the normal force. And we intentionally made it that way. We made the x-axis perfectly line up with acceleration so that there's no acceleration in the y direction. So we can, and that's on purpose. We called that a sub y 0. So we can bring mg to the other side, like we could add mg to both sides and say n equals mg cosine theta. So we just, from doing this strategy, we just figured out that the normal force equals mg cosine theta. That's information that we're going to now need for the other axis, the one that we're really interested in, right? And notice this, the normal force supports, it doesn't support the whole weight of the object. It supports mg times the cosine of the angle, i.e., when theta is 0, cosine is 1. So when theta is 0, then the normal force is fully supporting the weight of the object. But as the angle gets bigger and bigger, the normal force gets weaker and weaker. It's supporting the plane is supporting less and less of the object as the plane gets steeper, right? Okay. So we got that. So now we go to the other axis. We say, okay, on the other axis, just looking at our picture, we've got mg sine theta down and friction down. Together, they equal ma down along the plane. And that is acceleration. That's not 0. That's something that we're solving for. But we know, and this goes back to the Chris thing from the beginning of the class, we know that friction equals mu times the normal and whatever the mu is. So we substitute in mu times the normal for the friction. And the key point here, by the way, if you put aside all the technicalities of what I was saying about mu at the beginning of the class, the key point is whatever mu is a number, and it's the same whether we're going up or we're going down. I mean, whatever the number is, it's the same when you're comparing up to down. That's why the lab report works, or anyway, it's the same up and down. So friction equals mu times the normal. So we substitute that in, mu times the normal for friction. So now we could say mg sine theta plus mu times the normal equals ma. But we went to the y-axis and analyzed what the normal force was. The normal equals mg cosine theta. Not in life, not all the time. You definitely cannot memorize that. You'll see in 2 minutes. It won't even work in 2 minutes. But it works in this coordinate system, in this analysis, that the normal equals mg cosine theta. So mg sine theta plus mu times mg cosine theta equals ma. You factor out an m, divide both sides by m, cancel them out, and we have that equation for the up trip. And then, and just to wrap up what you do in the lab report, that's the equation for the up trip, and all of those are numbers that can be plugged in, like theta because you measured in lab, mu, g, or you make up whatever, and then you compare that to the down trip. The down trip is all the same, except there's a minus sign instead of a plus sign in there. So this then gets back to what I was saying last Wednesday. I'm not going to repeat it now in detail, but you could see that the forces are working together when the object is going up. The forces are working against each other when the object is coming down. So the acceleration on the way up is actually greater than the acceleration on the way down. Therefore, the average velocity is actually greater on the. Now I'm doing this fast partly because I already said it Wednesday, partly because I think this is the part you're not confused on. I don't know, but this is what you want to show in the lab report, that given those two expressions for A, and you would have had to have done a whole nother diagram for the down trip that I just skipped right now because I think you can do that. But you compare the two pictures, you get the two F nets, you get the two A's, and you say here, even though it was a surprise that the thing quickly went up and then slowly came down, here's why that happened. And in the end of the day, in English, what we're saying is the object lost velocity on the way up at a more rapid rate than it gained velocity on the way, or I shouldn't even say velocity, speed. The object lost speed more quickly on the way up than it gained speed on the way down. That's really what we're saying. I mean, it's a mouthful. You got to think about it. Like, yes, hello, physics. But that's what we're saying. It gained speed. No, it lost speed on the way up at a more rapid rate than it gained back that speed on the way down. So it actually got up faster than it came down. But now what I want to say, like, all of that makes total sense. Like, once you think about it, I mean, I think it makes sense once you really think about it. And once you say, like, okay, mg sine theta plus mg cosine theta versus mg sine theta minus mg cosine theta. But all that falls into place if you do the diagrams the way we just did them. And at first, it seems weird to do the diagrams that way. It seems weird to break up gravity, and it seems hard to know whether it's sine or cosine for gravity. So the question is, well, wait a second. Are we just like pulling stuff out of our, like, are we like, how are you supposed to know this? Or like, why do physicists do stuff like this? Question with 12 minutes left, with 11 minutes left is, could we have just been like normal people and just walked into this and just said, you know, hello, this is an x-axis and this is a y-axis. And I always learned that in math. And I always learned that cosine goes with x. And can't I just freaking keep my x-axis and y-axis like this? And can't I just say gravity is a nice little vector that's pointing down? And can't I just break up the normal force? Like, why can't I do that? Yeah, wouldn't that be? And I'm going to show you. We're going to do, and you are responsible for it. We're going to pretend there's no friction. Don't even worry about the friction. It's hard enough without. We're going to say, here's our pure FB, and you're responsible for this. I know we have 11 minutes, but I'm showing you the contrast. I'm showing you the depth of physics here. I'm trying to. Here's our pure free body diagram. Normal going like that, gravity going down. What if we chose a customary coordinate system, a horizontal vertical coordinate system, and then in other words, decided to break up the normal instead of gravity? Could we do that? And the answer is totally yes. And that's what I'm going to do right now. If we break up the normal instead of gravity, then we zoom in on the normal force. We zoom in on the normal force, and we say that it has two components. One's a sine, one's a cosine. But if we think about it, and I'm doing this a little bit fast here, and I've already drawn the pictures. If we think about it now, the normal force, the angle in the normal force triangle, the angle that is theta, the angle that is the same as the angle that was given in the original triangle is this angle right here, not the one at the base. How do I know that? Very quickly, because theta at the base of our inclined plane is an angle between, like, well, is this angle right here. That is, unless it happened to be 45 degrees, there's no reason. It's the complement of an angle that is drawn if you make your hypotenuse, your diagonal, go exactly the other way, right? Like I can't, you'll have to think about it. But if you think about it, you'll see that, like, if you draw like alternate interior angles or whatever, like the angle that's drawn between the upright going plane and the horizontal is definitely not the same as the angle going from an up left hypotenuse. It's the complement of that. So in other words, if you took your inclined plane and you rotated it, and you rotate the whole plane 90 degrees, yeah, just rotate your whole plane 90 degrees to the right, you'll see that your original angle of inclination ends up on the top right here. So the side across, so think about that, but it's true. The side across from it is the horizontal side. So the horizontal here gets sine and the vertical gets cosine. Again, this is exactly going to Chris's question from the beginning of class. And it was not a stupid question. It's like a really important question because everybody would think that sine always goes with x and and that's like basically what you were trained to think from unit circles. But it turns out, no, it depends how you draw your triangle. In this case, the theta is up there. So x is across from it. And so the components are n sine and n cosine like that. So if I put them into the triangle, and you could do my trick before, ask yourself which one should disappear when theta is 0. When theta is 0, the normal is pointing entirely up. When theta is 0, the track doesn't push the marble to the left or to the right. It only pushes it up. So the horizontal component disappears when theta is 0. So it gets a sine because sine of 0 is 0. Anyway, here's our diagram then. We got n sine pointing horizontally and cosine pointing vertically, mg pointing down. So now I'm going to apply F net equals ma with 7 minutes to each of the axes, just like I did before. It doesn't seem that bad, right? Maybe it even seems, and I'm not even worrying about friction. You're going to see even without friction, you'll see what happens. Then you can put in the friction at the end if you want. So I'm going to say, okay, I'm going to look at the y-axis. And I'm going to call whatever's going down, I'm calling positive because I know the thing is sliding down. So I'm calling this positive and I'm calling down also positive. So in the down direction on the y-axis, mg down minus n cosine theta up equals ma sub y. But here's the thing. I can't cross out that a and call it 0 anymore. Since I didn't line up the x-axis with the acceleration, that means, right, since this is an axis and this is an axis, the ball is accelerating along a diagonal. It's accelerating somewhat to the left and somewhat down. It most certainly is accelerating somewhat down. And so I've got to break up the acceleration vector. I don't want to do that any more than you do, but I have to if I didn't line up the x-axis with the acceleration vector. So the acceleration vector has two components, a sine and a cosine. So this direction is sine. So I have a statement, mg minus n cosine theta equals ma sine theta, right? And that's all I can say for that. Now I go to the other axis. Well, that's what I say for that. I just rewrote it. Yeah, I just rewrote it on the next page. Now I go to the other axis. The other axis, there's only one horizontal force. I mean, like the x-axis, there's only one force. It's n sine theta. So n sine theta equals ma cosine theta. Like A has to be broken up now because, right, A has two components. So n sine theta equals ma cosine theta. So a big part of my lesson here is that the problem with this coordinate system is we got to break up acceleration too. So we're breaking up two things now instead of just one. Plus, we'd have to break up friction if there was friction here. So what do I do now? I've got the unknown that I'm solving for is A. I'm solving for acceleration, but I've got this other unknown, N. Two equations, two unknowns. What I'll do is what I always do, arrange things so that I can just solve for N and in effect plug in or substitute or whatever. So I'm going to rearrange each equation so I can write it as an expression for N. Like the bottom one, I just divided both sides by sine theta. So N equals ma cosine theta over sine theta. But I'm going to do the same thing to the other equation. I just rewrote it at the top, mg from the other axis. So I got the N term by itself and then divided both sides by cosine theta. So now I have two different expressions for N, one that came from the x-axis and one that came from the y-axis. So I set them equal to each other because I don't care about N. I'm just trying to get rid of it so I can solve for A. So I set my two expressions for N equal to each other, mg minus ma sine theta over blah, blah, equals that. All right. And now I have to solve for A, right? Solve for A. There's A in the left and there's someone on the right. So there's some algebra I got to do here. I got to do some serious algebra here. What I'm gonna do is multiply both sides by cosine, and I'm gonna multiply both sides by sine, so I can get a whole bunch of terms, and I can collect the A terms. In other words, I did it right. First I divided both sides by m. Sorry, I factored out an m, divided both sides by m, so I got rid of the m's. So now I have g minus a sine theta over cosine theta equals a cosine theta over sine theta. By the way, when we're done, if anybody needs me to go back to any pages, of course I will. So now I multiply both sides by cosine theta and multiply both sides by sine theta. So I get g sine theta. I'm just like distributing a sine theta to the, I'm cross multiplying. So g sine theta minus a sine squared theta equals a cosine squared theta, right? So then I collect all the a terms because a is what I'm solving for. So I bring the a to the other side and I have g sine theta equals a cosine theta plus a sine squared theta. And this looks like a mess. But then I factor out the A. And does anybody remember? We've got 3 minutes left. This is perfect time. We are just about done. Does anybody remember from math class? Wait. Okay.
Isn't it one?
Yeah.
Yes. And how perfect that Melita of all people would, yes. Awesome. And I got the private chat person. Yes. Thank you. Yes, Melita, it's totally one, which is awesome. So this whole big mess, that's great. And your math, I'm going to tell your math professor right now. Yes, it equals one, which is yes. I'm so psyched. So g sine theta equals a times 1, which means g sine theta, which means a equals g sine theta, which it freaking better because that's what we showed at the beginning of class. It totally did with the other way of doing things. What I'm trying to say, and we've got like 2 minutes left. What I'm trying to say is that we could do either coordinate system we want, and they'll work. They'll work out to the same result, which is that a equals g sine theta. But yeah, that's funny. But this one is a lot more algebra to do, crazy algebra. It's a lot more sines and cosines. And remember, this one, I didn't even include friction. If there were friction in here, there'd be even more sines and cosines because friction would also be broken up. So the other way, where it looks weird to break up gravity, it is a little weird to break up gravity, but by breaking up gravity, it's all you have to break up, and you don't have to break up A. That's the key point. And so on one axis, A automatically equals 0. You can balance forces right away, and boom, boom, and then you just see it. With this, you could do it this way, and physics is still right, but this is a mess. So, and she's back. Okay. And so the big lesson of this, again, is what everybody knew from the start, which is that the issue of physics is not doing the math. The issue of physics is setting up the math. But how do we set up the math? We make conscious choices about what coordinate system we're using. Oh, cool. We're making conscious choices about what coordinate system we use. All coordinate systems will get the same answer, but some coordinate systems will be a lot more convenient. And when it comes to forces in F net equals ma, the strategy I'm saying, and it will come up again in Physics 204, honestly, the strategy is you choose an x-axis that lines up with expected direction of acceleration. You line up plus x to line up with plus y, and then your math will be easier than any other way you could do it. That's the lesson of this. Okay, and wow, it's 4:20. So I'm not going anywhere. If there's any questions or you want to like go back pages or whatever, I'm totally here. But other than that, I really appreciate all the questions and the participation. So have a great Thanksgiving, and there is no new homework, even though there should be, but there isn't. And then you can thank Felix for that. Okay. Happy Thanksgiving. Yes. Okay, so I'm stopping the recording, but I'm still here.